Astronomers closely monitored an interstellar object known as 3I Atlas as it moved through our solar system. And the collected data strongly suggests it is not a typical comet. The object emitted jets aimed directly toward the Sun while rotating once every 16 hours. Yet those jets remained fixed in orientation instead of spreading out through space, as physics predicts they should. Its composition revealed unusually pure, industrial-grade nickel with almost no water content. Even more puzzling, when it accelerated near the Sun, the body stayed solid and intact instead of fragmenting the way icy comet nuclei usually do. This raises an unsettling question. Can a frozen comet really generate stable jets that seem unaffected by solar wind and known physical processes? Or is 3I Atlas something else entirely, possibly technology disguised as a natural object? The impossible path that looked planned 3I Atlas entered the solar system on a trajectory that immediately made astronomers uneasy. It followed a retrograde orbit, moving opposite to the direction in which planets circle the Sun. Even more striking, this backward path was aligned within 5 degrees of the ecliptic plane, the narrow region where most major planets orbit. Statistically, the chance of a random interstellar object arriving with this precise alignment is about 0.2%, roughly 2 out of 1,000. That alone is unlikely, but the timing makes it even more suspicious. 3I Atlas arrived at just the right moment to pass within tens of millions of kilometers of Mars, Venus, and Jupiter. 2 of those worlds lie in or near the habitable zone. And Jupiter hosts moons like Europa and Ganymede that contain subsurface oceans and are considered prime candidates for life. For a random interstellar traveler to encounter several potentially life-friendly targets in a single pass would require extraordinary luck. Put another way, imagine throwing a rock blindly from another star system toward our solar system. What are the odds it would arrive exactly on the same plane where all the most interesting planets orbit, and at precisely the right time to closely approach 3 of them? The calculations suggest this would occur only about 5 times in a million attempts. Those are not comforting odds if randomness is the explanation. The timing of perihelion adds yet another layer of suspicion. When 3I Atlas reached its closest point to the Sun on October 29, 2025, it positioned itself almost perfectly opposite Earth. From our vantage point, the object vanished into the Sun's glare during the exact period when its velocity and direction changed. Astronomers lost visual contact during the most critical phase of its journey. The moment something important happened was the one moment we couldn't observe it directly. However, ESA's ExoMars Trace Gas Orbiter, watching from Mars orbit, was able to monitor the object during this hidden window. Their measurements showed changes in velocity that could not be fully explained by solar radiation pressure or standard cometary outgassing. The shift occurred precisely when Earth-based telescopes were blind, almost as if the timing had been chosen deliberately to avoid observation. NASA's Atlas Survey Telescope in Chile first detected 3I Atlas on July 1, 2025. Within hours, astronomers realized something was wrong. The object was not following a normal curved orbit bound to the Sun. Instead, it was on a hyperbolic trajectory, appearing nearly straight as it passed through the system. Its orbital eccentricity was measured at 6.139, the highest ever recorded for any visitor to our solar system. Such an extreme value means the object was moving fast enough to escape the Sun's gravity entirely without slowing down. Its speed supported this conclusion. 3I Atlas entered the solar system at about 58 kilometers per second relative to the Sun, around 130,000 miles per hour, nearly twice the entry speed of Oumuamua, the first confirmed interstellar object discovered in 2017. By the time it reached perihelion on October 29, gravity had accelerated it to roughly 153,000 miles per hour. Objects formed within our solar system simply do not move this fast unless something actively propelled them. The direction of arrival adds yet another anomaly. 3I Atlas came from the region of Sagittarius, near the center of the Milky Way. Its path carried it close to Mars on October 3rd before it slipped behind the Sun, where Earth-based observatories again lost track during the most crucial part of the encounter. Mars was about 29 million kilometers away during this pass, close enough for detailed observation. yet far enough to avoid gravitational disturbances that could have disrupted the object's carefully tuned approach toward the Sun images taken. Before its official discovery by the Zwicky Transient Facility revealed that the object was already active as early as May 21st, 2025, when it was still beyond Jupiter's orbit. Ordinary comets do not begin releasing gas at such distances. They usually remain dormant until much closer to the Sun, where heat can vaporize surface ice. 3I Atlas, however, started producing a visible cloud at around 9 astronomical units from the Sun, exactly where carbon dioxide ice begins to sublimate. The timing was remarkably precise, almost as if the object knew when to activate in order to resemble a natural comet. Specialists in orbital dynamics find these coincidences deeply unsettling. The trajectory resembles less a piece of random debris and more a carefully calculated approach designed to encounter multiple planets while remaining hidden during key course adjustments. When you combine a backward orbit, near-perfect planetary timing, and a concealed velocity change, the coincidences begin to feel less accidental and more intentional. And this is before considering the chemical signature that truly separates 3I Atlas from every comet ever studied. The chemical makeup that doesn't make sense. Spectroscopic studies revealed a composition that left experienced astronomers uneasy and caught the attention of materials scientists. 3I Atlas contains unusually high levels of nickel, with a nickel-to-iron ratio that closely matches manufactured alloys rather than naturally formed space rocks. Its nickel-to-cyanide ratio is orders of magnitude higher than any known comet, including 2I Borisov, the only other confirmed interstellar comet ever observed. The lack of water is just as troubling. Typical comets are essentially dirty snowballs, dominated by water ice that drives their activity when heated by the Sun. In contrast, 3I Atlas appears to contain only about 4% water by mass. That is completely inconsistent with standard comet models. Instead, carbon dioxide and carbon monoxide dominate its emissions. While these gases can sublimate farther from the Sun than water, they do not provide enough energy to explain the object's brightness and the size of its surrounding cloud without consuming material at unrealistically high rates. To make the problem clearer, imagine discovering a car that runs on orange juice instead of gasoline. Yes, it is technically a liquid, but it lacks the energy density needed to power a vehicle efficiently. That is the situation with 3I Atlas. The observed fuel does not match the performance. The nickel signature, in particular, resembles industrial processes used to create pure nickel coatings, processes that require tightly controlled temperatures and pressures not known to occur naturally in comet-forming regions of space. Laboratories have spent many decades perfecting nickel carbonyl cycles for producing heat shields and components that must survive extreme temperatures inside engines. No one is suggesting that 3I Atlas is operating a metal refinery in space, but the chemical signatures it carries resemble tightly controlled industrial methods far more than the random processes of freezing and sublimation expected in deep space. Polarization data introduces another unsettling clue. Light reflected from 3I Atlas follows patterns that point to dense, smooth surfaces rather than the loose, fluffy, highly porous textures normally associated with comet nuclei. Compact surfaces with low porosity scatter light in a very different way and also retain heat differently, which fundamentally alters how jets form and how material escapes into space. If the surface is not a mix of dusty ice and voids, then what is it, and why does it behave more like engineered thermal shielding than natural cryogenic sludge? As it approached perihelion, 3I Atlas brightened more rapidly than any comet on record and displayed a color that was noticeably bluer than the Sun. That blue hue implies smaller particles or unusual surface materials reflecting light in rare ways. The rate of brightening exceeded predictions based on standard comet chemistry and solar heating alone. Something about the way this object reflects light and sheds material simply does not fit within the normal comet framework. What makes these observations especially disturbing is how they connect to the next set of findings. The jets are not just chemically strange. Their behavior appears to violate basic physical expectations. The jets that broke every rule images collected by several observatories revealed narrow jets aimed straight toward the Sun. stretching nearly 1 million kilometers while remaining tightly confined. 3I Atlas spins once every 16.16 hours, meaning that any opening on its surface should rotate through sunlight and darkness like a sprinkler turning in circles. That motion should produce a spiraling jet with obvious pulses or bead-like structures, spaced at regular intervals. No such pattern was ever observed. Data from November 9, 2025, collected by astronomers Nebling and Berner, showed sharply focused jets extending beyond 1 million kilometers. At typical cometary outflow speeds of around 400 meters per second, gas would need roughly a month to travel that distance. Over that time, the nucleus would complete dozens of rotations. How, then, do the jets maintain a fixed direction without smearing or breaking apart? The numbers simply do not add up. To understand how strange this is, picture yourself rotating once every 16 hours while holding a garden hose that sprays water at a steady speed. As you spin, the stream would naturally form a curved or spiral pattern in the air. Now imagine that the water somehow remains in a perfectly straight line, unaffected by your rotation. That is essentially what 3I Atlas appears to be doing, and it contradicts the basic physics of rotating bodies expelling material. The Hubble Space Telescope captured high-resolution images on July 21, 2025, revealing the object's teardrop-shaped cloud in striking detail. The symmetry and precision of the outflow do not resemble chaotic gas leaking from an irregular, tumbling ice mass. Instead, it looks more like a directed stream emerging from a nozzle designed to keep thrust aligned in a single direction. Engineers familiar with spacecraft propulsion immediately recognized this pattern: steady exhaust with minimal dispersion, characteristic of controlled mass flow rather than random venting caused by uneven heating. The only explanation that matches all the observations without relying on a long list of unlikely assumptions is that the jets maintain their orientation through some form of active control. One possibility is a rotating outer frame or cage that holds the emission points fixed while the internal body spins independently. Similar to how spacecraft use gyroscopes to keep their orientation stable even as internal components move. That explanation may sound simple, but it aligns cleanly with observations that stubbornly refuse to fit passive ice-space models. No exotic temperature maps are required. No carefully tuned shadow effects are needed. Just active stabilization doing exactly what active stabilization is designed to do. Specialists in rocket propulsion are deeply uneasy with claims that natural gas release can generate tightly focused thrust over million-kilometer distances while completely ignoring a 16-hour rotation cycle and intense solar radiation pressure measured in thousands of watts per square meter. The mathematics works when you assume directed systems with nozzles engineered to hold thrust orientation. The same equations collapse when applied to porous ice, where vents fire in multiple directions and solar wind shreds any sunward stream within the first few thousand kilometers. When a natural explanation only works after stacking 5 special conditions on top of each other, it becomes reasonable to ask whether the simpler explanation might actually fit better. But there's one last piece of evidence that pushes this discussion beyond speculation and firmly into physics. And it occurred at the exact moment Earth was unable to watch. The hidden burn that changed everything tracking data revealed velocity changes that orbital prediction software could not dismiss. 3I Atlas deviated from a purely gravity-driven trajectory by an amount that requires additional forces beyond the sun's pull. If that extra push came from ordinary cometary outgassing, the object would have needed to lose at least 13% of its total mass. That level of mass loss normally shreds fragile comet cores or leaves unmistakable signs of breakup, fragment clouds, chaotic tumbling, or long debris trails. None of that was observed. 3I Atlas passed through perihelion intact, with no fragments, no erratic spin behavior, and no expanding debris field. The acceleration occurred mainly while the object was hidden behind the sun from Earth's viewpoint, lost in glare where precise tracking becomes impossible. Once it emerged after perihelion and returned to visible skies, its trajectory snapped back into a smooth, predictable line, as if a controlled maneuver had ended and the object had resumed cruise. The magnitude of the speed change exceeded anything seen in natural comets. Except for sungrazers that plunge within a few solar radii and absorb thousands of times more heat than 3I Atlas ever experienced at its closest distance of roughly 203 million kilometers. When the tracking residuals are plotted over time, the pattern resembles brief, steady thrust followed by coasting, not the noisy, irregular signature of random vents switching on and off as sunlight shifts across a rotating surface. What makes this even more compelling is the role of ESA's ExoMars Trace Gas Orbiter. Data from Mars orbit improved trajectory predictions by a factor of 10 compared to Earth-based measurements alone. That dramatic increase in accuracy came from triangulation using a different viewing angle, which stripped away uncertainties that could have hidden subtle effects. With cleaner data, the non-gravitational acceleration becomes impossible to ignore. It stands out sharply once measurement noise is removed. The fact that the object remains structurally intact after perihelion is the real smoking gun. Porous icy bodies that shed more than 10% of their mass rapidly tend to fracture, develop new active regions, or begin tumbling as uneven mass loss introduces twisting forces. 3I Atlas did none of this. Its structure remained stable, and its path smoothed out as though whatever provided the speed increase was designed to do so without damaging the platform. Ice does not behave that way when it loses that much material that quickly. Classic comets can display dramatic accelerations when they skim extremely close to the sun, where thermal stress becomes overwhelming. Internal ices boil explosively, shapes deform, and orbits twitch unpredictably. But 3I Atlas never ventured that close. Its perihelion distance kept it well outside the zone where solar heating acts like a hammer. The energy accounting simply does not balance. The sunlight it received cannot explain the observed acceleration without consuming a large fraction of the object's mass. Yet post-perihelion observations show no evidence of such loss. The structure appears unchanged. The rotation remains steady. No debris trail emerges. It is like watching a vehicle surge forward without burning fuel. The final, most damaging detail is the precision of the trajectory after the event. Once past closest approach, 3I Atlas returned to a path that matched predictions made before perihelion, as if a guidance system executed a planned maneuver and then shut down. Natural gas release produces messy, ongoing deviations as different surface regions heat and vent unpredictably during rotation. 3I Atlas behaved like a spacecraft that fired thrusters during a calculated window and then turned them off. Clean start, clean stop, clean return to the expected course. Experts who analyze spacecraft maneuvers recognize this signature instantly. When you plot the difference between predicted and actual positions for a spacecraft performing a burn, you see steady acceleration during the burn followed by a return to ballistic motion afterward. 3I Atlas shows precisely that pattern. Perform the same analysis on a natural comet, and the result is chaotic noise that fluctuates in strength and direction as the body tumbles and vents shift. 3I Atlas does not display that noise. It shows a profile consistent with deliberate thrust. The location of the maneuver matters as well. It happened behind the sun, where Earth cannot observe it. If you wanted to adjust your trajectory through the solar system without being seen by the one planet equipped with the most advanced telescopes, that is exactly where you would do it. The fact that the largest velocity change occurred in Earth's blind spot, while a Mars-based orbiter captured partial data from another angle, feels less like coincidence and more like informed timing. 12 independent anomalies now form a case that resists conventional explanations. A trajectory aligned with the ecliptic, time planetary encounters, and a perihelion passage hidden from Earth. A chemical makeup resembling industrial nickel alloys with minimal water. Jets spanning 1 million kilometers that ignore rotation and solar radiation pressure. A non-gravitational acceleration during Earth's blind spot, followed by structural integrity and a resumed trajectory. Each anomaly can be forced into a natural explanation if enough adjustments are made. Exotic thermal behavior that never pulses. Unusual chemistry that just happens to mimic industrial processes. Structural strength that contradicts typical comet fragility. Jets that somehow forget rotation physics. Stack them together, and the natural model requires more patches than the alternative. Skeptics rightly demand extraordinary evidence for extraordinary claims. But the real question is what qualifies as extraordinary when a dozen separate observations all point in the same direction? What does skepticism mean when critics dismiss anomalies by comparing them to comets operating at different distances, with different spin rates, under entirely different radiation conditions? The next interstellar visitors will provide the decisive test. NASA's Atlas system and the Vera Rubin Observatory are expected to detect dozens of interstellar objects in the coming decade. If 3I Atlas is a singular oddity, it will fade into history as one of nature's rare tricks. If directed interstellar probes are passing through our neighborhood, future surveys should reveal more objects with the same telltale features. The issue is not whether we prefer natural explanations or engineered ones. The issue is whether we are ready to recognize the truth at full speed when the sky offers another chance. 3I Atlas challenges habits more than physical laws. Gravity still governs motion, and sunlight still drives chemistry. But the timing, the order, the composition, the jets, and the thrust together tell a story that no longer fits comfortably in the old framework. So what do you think? Is 3I Atlas simply the strangest comet ever recorded? Or is it something entirely new? Share your thoughts below. And if you want updates when the next interstellar visitor enters our skies, be sure to subscribe.